Today's documentary, Quantum Underdogs, Building the Future Atom by Atom. In a modest laboratory in Sydney, in the year 2018, a decade of work came down to a single, silent moment. A team of scientists huddled around a monitor, their world compressed to the flicker of a line on a screen. They were about to run a test on the world's most precise quantum processor. Not at Google's sprawling quantum AI campus in California, not in IBM's vast research complex in New York, but here at the University of New South Wales. Their rivals had billions. They had a belief, and etched into a sliver of silicon, just a few nanometers across, were the delicate quantum states of individual phosphorus atoms. They had staked everything on a radical idea: to build a quantum computer one atom at a time. This is the story of the ultimate scientific underdog. Rewind to the beginning. The global quantum race was heating up, but the map looked nothing like it does today. In the early 2000s, the giants were barely on the track. The dominant theory was that quantum bits, or qubits, the heart of a quantum computer, would be built from exotic, fragile materials. Superconducting loops, trapped ions, photons. They were dazzling, but delicate, requiring temperatures colder than deep space and immense isolation. It was a bottom-up approach, coax quantum behavior out of complex, finicky systems. Meanwhile, in a quiet corner of the southern hemisphere, a physicist named Michelle Simmons was looking at the problem from the opposite direction. What if the answer wasn't something new, but something ancient? The very bedrock of our digital age, silicon. Her vision was breathtakingly direct, almost arrogant in its simplicity. Instead of building up, they would sculpt down. They would take a piece of ultra-pure silicon and, using a scanning, tunneling microscope as their chisel, they would precisely place individual phosphorus atoms into the crystal lattice. They would create qubits from the ground up with atomic precision. This was a top-down approach of unparalleled ambition. But to do it, they would need to see and move single atoms. They would need to become the world's finest atomic architects. The first monumental proof arrived in 2012 in a paper published in the journal Nature Nanotechnology. The headline said it all: a single atom transistor. The team, led by Martin Fuchsel, a postdoc in Simmons's center, had done the impossible. They had patterned a channel in silicon with such precision that they could control the flow of a single electron through a single phosphorus atom. It was a masterpiece of control. The global scientific community took notice. But the accolades masked a brutal reality. Funding in Australia for such blue sky, long-term research was a constant struggle. While Google and IBM could pour hundreds of millions into parallel approaches, Simmons's team was fighting for every grant, every piece of equipment. They were racing against time, and the clock was being funded by competitors with seemingly infinite resources. The narrative forming in the tech press was clear: the quantum future would be forged in the giant industrial labs of North America. The Australian work was seen as beautiful, elegant science, but perhaps a boutique solution, too slow, too precise to ever scale. Doubts crept in, even within the team. Were they on a fool's errand? Perfecting atomic placement was painstaking work. A single day of vibration from construction nearby could ruin weeks of effort. The emotional toll was immense. Simmons, driven and fiercely protective of her team, became a relentless advocate, shuttling between Sydney and Canberra, making the case not just for funding, but for the very viability of their vision. Then, a critical pivot. The single-atom transistor was a marvel, but a quantum computer needs qubits that can talk to each other, that are entangled. The challenge was quantum mechanics at its most fiendish. The quantum state is notoriously fragile, collapsing if it so much as glances at the outside world. Isolating one atom was hard. Isolating two, and making them interact in a controlled way, was considered by many to be the brink of impossibility with their technique. For years, they inched forward. PhD students burned out. Postdocs moved on. The valley of death between a scientific prototype and a functional device loomed large. Breakthrough often comes from a side door. A key insight came from addressing a fundamental problem: how to control these atomic qubits without drowning out their quantum signal. The team developed a new method of control using simple microwave pulses, similar to those in a mobile phone, but exquisitely tuned. The pieces were falling into place: atomic placement, single electron control, and now, coherent manipulation. They were learning to conduct a quantum symphony at the atomic scale. The crescendo built towards late 2018. While the world buzzed about quantum supremacy and the raw power of superconducting qubit counts, the UNSW team focused on a different metric: accuracy. That year, they announced not one, but two landmark achievements. First, a single qubit gate fidelity of 99.96%, a world record for any type of qubit in silicon. Then, the culmination, a two-qubit logic gate, the fundamental operation of a quantum computer, performed with 98% fidelity. Their processor, built from just two atomically placed phosphorus qubits, was the most accurate of its kind on the planet. Today, the laboratory in Sydney is a hive of activity, aiming for a 10-qubit quantum integrated circuit, etched atom by atom. Their race isn't just about building a faster computer. It's about proving that the future can be built with intention, atom by precise atom, from the silicon ground up. Thank you for watching. If you enjoyed this documentary, please subscribe to our channel. We bring you fascinating documentaries on history, science, civilizations, mysteries, and the untold stories that shaped our world. Hit the subscribe button and the bell icon so you never miss a new release. See you in the next one.